Hello everyone. In this video we will be discussing rotational kinematics. A lot about how we do the calculations in this unit are much the same as how we handled things back during the linear kinematics unit. In fact, other than some new terminology for objects rotating or going in circles, the equations are structured exactly the same way. Instead of linear position x, we have angular position theta, which tells us about the current angle an object is located at, or by what angle the object has spun in radians. Rather than linear velocity, we have angular velocity, which measures how fast an object is spinning, or in other words, how many radians each second the object has passed through. And finally, instead of linear acceleration, we have angular acceleration, which describes how quickly our angular velocity is changing in radians per second squared. Each of these angular quantities can be changed back over to their tangential or linear equivalent by multiplying by the radius of your rotational motion. Let's go through a multi-part question to see how rotational kinematics works and how it connects back to linear quantities. Our sample here says a CD starts spinning from rest with a constant angular acceleration. It reaches its maximum angular velocity of 200 rpm in 2 seconds. Part A asks us to find the angular acceleration of this CD. Just like we did back during linear kinematics, we can start these types of problems by listing all the quantities that are relevant to see what all we do know and what all we don't know, as well as pick out whatever the best question is to find what we are looking for. For rotational kinematics, we might want to think about what angles we are at initially and finally. This problem doesn't seem to give us any angular information at the start or finish. However, just like we did in linear kinematics, we can call the arbitrary starting point of this problem at a theta initial of 0. However, we don't have any information that tells us about the final angle. Next, we might want to think about the angular velocities, both initial and final. We're told that the CD starts spinning from rest. That is, it starts not rotating at all, so its initial angular velocity should be 0. Then we are told that it reaches a maximum angular velocity of 200 rpm. Now, thanks to the wording of this problem, it's pretty clear that this is an angular velocity that they're giving us. However, recall that we want our standard units of angular velocity to be in radians per second, whereas this rpm stands for revolutions per minute, which is to say every minute the CD will spin 200 times. This isn't the unit we want our omega in, so we will have to do some conversion here. Fortunately, in this unit we are provided a conversion rate between RPM and radians per second. So doing our conversions, putting 200 RPM over 1, we need to multiply by a fraction that puts this conversion into a unit fraction. We want the 1 RPM on the bottom to cancel out the RPM, which means the 0.105 radians per second goes on top. Doing this conversion gives us exactly 21 radians per second. So this will be what we use for our final angular velocity. Next, we might think about the angular acceleration alpha, which is exactly what they are asking for in this problem, so let's make note that this is what we are looking for. And finally, time is involved in our equations. This question does happen to give us the time of 2 seconds. So looking at everything we know and what we are looking for, we will want to choose one of these kinematic equations to use. We know we want one that involves alpha, and probably not one that involves the theta final, which we don't know. It looks like we have enough information to use this top equation. So omega final equals omega initial plus alpha time. Plugging in, we get 21 equals 0 plus the acceleration, which we don't know, multiplied by time of 2 seconds. Going through the algebra, we get alpha equals 21 over 2, which will give us 10.5 radians per second squared. So there is our angular acceleration. Moving on to part B, a speck of dust rests 1 centimeter from the center of the disk. Once the CD reaches top speed, what arc distance would the dust travel in the time to play a song that is 3.5 minutes long? In this part of the question, the CD has now reached its top speed and is implied to be rotating at that constant rate of 200 RPM. So that means the angular acceleration that we found in the previous part is no longer relevant, and we actually have 0 as our new angular acceleration. This is because we are rotating at a constant speed now. Using that piece of information, we can go ahead and say that both the omega initial and omega final, our angular velocities, are both equal to the same 200 RPM, which again we would want to convert to that 21 radians per second. We are also basically restarting our measurements, starting the moment that the CD has reached its maximum velocity. So we can once again call theta initial our starting point equal to 0 radians. However, we don't know anything about the final angular position. And finally, our time will no longer be the 2 seconds from before. Now we are letting a whole song play that is 3.5 minutes long. That time is in minutes, which we would want to convert over to seconds. So taking 3.5 minutes, and since there are 60 seconds in every minute, our time in seconds ends up being 210. So there is our t. But now, what exactly are we looking for? This question is asking about the arc distance that this speck of dust travels. Arc distance is like measuring how far along a circular track you have run, or in this case, measuring how far this speck of dust has traveled going around the center of the circle. And the equation we use for arc distance is this s, which equals the arc distance, equals the radius of our circular motion, multiplied by the angle that the object has rotated through. Since delta theta is the same as theta final minus theta initial, if we can use rotational kinematics to get our angles, and make note that we are given the radius of this CD that the speck of dust is on, in this case our radius will be 1 centimeter, which we would want to convert over to 0.01 meters. So let's get started with the kinematics. We know we are looking for theta final, and we have plenty of other information to go around. So as long as an equation involves theta final, we should be safe. The easiest one to use might be the theta final equals theta initial plus omega initial times time plus 1/2 alpha times squared. Plugging everything in, we get theta final equals 0 plus 21 times the 210 seconds plus 1/2 times 0 for acceleration times the 210 seconds squared. Doing this calculation gives us a final angular position of 4,410 radians. This means that our speck of dust has traveled through theta final minus theta initial number of radians, which would just be the 4,410, which now lets us find our arc distance s by multiplying our radius of 0.01 meters by the delta theta of 4,410 radians, giving us a distance that this speck of dust has traveled of 44.1 meters. And finally, part C here asks, what is the minimum coefficient of static friction that will keep the speck of dust affixed to the CD? This one seems tricky, but it is combining a few previous topics together with rotational kinematics, so let's try to reason things out. We know we are looking for the coefficient of static friction, our mu subscript s, but the only equation we have that shows up in is the equation for static friction itself. This says that static friction force is less than or equal to the coefficient of static friction multiplied by the normal force. Since the only way to get to our coefficient here involves the force of friction, maybe we should go back to force diagrams. First, I'll draw an overhead view of my CD. Here is the speck of dust, which is 1 centimeter away from the center. And as it spins in some direction, what forces are going to be acting on it? We know there's going to be some kind of friction force here, but what direction will that point? Well, if the speck wasn't affixed to the CD, it would just be flung off in the tangential direction. So since that doesn't happen, there must be a force keeping it from going off in that direction. In order to maintain the rotation, friction must be keeping the speck of dust from just flying out radially, so there must be an inward radial force of friction. Meanwhile, presumably we are on Earth, so we should have some gravity here, but which direction will that point? Well, right now we are looking at this CD from overhead, which makes it a little hard to draw gravity since it always points vertically downward. So maybe let's look at our CD from the side. So here's our CD with the speck of dust some distance from the center. Gravity is going to pull straight downwards. And since the speck of dust doesn't just fall through the CD, it must be experiencing a normal force from the surface of the CD. Going back to our unit on uniform circular motion, if this speck of dust is in fact going in a circle, we know that the sum of all the radial forces has to equal mass times velocity squared over the radius. Thanks to our force diagrams here, it looks like the only radial force inwards is the force of static friction. So that tells us that whatever the force of static friction is, it must be equal to mv squared over the radius. Since the question is asking about the minimum coefficient of static friction, the minimum coefficient occurs when it would be exactly equal to the static friction that we require here. So we can safely substitute the coefficient times the normal force into our static friction on the left side. And this still equals mv squared over r. This brings us to an equation which we now might be able to solve for the coefficient of static friction, but let's think about if we have everything that we need so far. The radius we know is just 0.01 meters. However, it looks like we also need the mass of our speck of dust, the linear or tangential velocity that the speck of dust is moving at, and also the normal force that the speck is experiencing. It looks like a lot of things that we don't have yet. But going back to our force diagrams, looking at our side view again, we see that the only vertical forces are the normal force and the gravity, which means they must be balancing each other out, telling us that normal force must be equal to mg. So while we still don't have m, that is a replacement we can make for the normal force. Meanwhile, the linear or tangential velocity of a rotating object has a relationship to its angular velocity, which is r omega. For this problem, we know things are rotating at a constant angular velocity, which we can plug in along with the radius. This ends up giving us a tangential velocity of 0.21 meters per second. So while we still don't have the mass, let's see what happens if we start trying to plug things in now. Our coefficient is what we're looking for. Normal force becomes m times g, which is 9.8, equals mass we still don't know, but the velocity we now know is 0.21. That gets squared over the radius, which is 0.01. And since we replaced the normal force with mg, now an m is multiplying on both sides, which means if we divide it, it cancels out on both sides. We didn't actually need the mass of this speck of dust to solve this problem. Going through and doing the algebra, we end up finding that the minimum coefficient of static friction has to be equal to 0.45. So here's our answer, and we have seen how rotational kinematics can connect back to several topics that we have discussed up until this point.